Okay. Hi guys, good morning. See you all again. It's today.
Morning, sir.
Morning.
Good morning, sir.
Morning. So we have almost 10 people with us. And we'll just do one more minute so that people join. Start. Okay. I think we'll start. Screen. Okay. So guys, no, not this one. Yeah. Yesterday's class. Hope you remember what all we saw. We spoke about this percentage yield, if you can remember, right? So everything is going to be same. You have to find the excess reagent, limiting reagent, everything is same, except that at last, whatever you have calculated is for 100% or for certain percentage, what will be the amount? That's what you have to do, only thing extra. Okay, maybe we'll just do one more problem based on this and then we'll continue with the next concept. A minute. Don't have such kind of problem, but we'll do a little bit, you know. I should have just one question. Okay, fine, no issues. If that's not there, no issues. Okay, let us solve this question. Here in the question, please. So today is our 11th. It's 4. 0, 7. Okay, now end on the question. 1.947 1.947 grams of iodine, I2, was allowed to react with 1.947 grams of iodine, was allowed to react with 1.056 grams of tin, SN. Okay, and these two to react to form, right? So 1.947 grams of iodine was allowed to react with 1.056 grams of tin to form SNXIY. Okay, Xn basically it's like Al2O3, something like that. SNXIY, right? Sn is the tin, X is some number, I is iodine, Y is some number. Okay, to form SNXIY along with 0.601 grams of 0.601 grams of unreacted SN. Unreacted SN. Right? So I want to know what is X and what is Y. Okay? Right? So I'll repeat the question, people. 1.947 grams of iodine reacts with 1.056 grams of tin to form SNXIY and 0.601 grams of unreacted SN. And the question is find X and Y. Go for it. I'll give you some 5 minutes. Work it out. So from this statement, 0.601 grams of unreacted SN, what can it decide? What is told by this statement? 0.601 grams of unreacted SN means what? What do you understand from the statement?
The reaction is not complete.
Reaction is not complete. No, this is
Sir, it
not
is
with
a residue or precipitate.
Sorry.
Sir, it's not 100% reaction, sir.
No, this is not that case. The reaction is 100% complete only. But what does this say? Like
Excess
crystals?
SN is
Correct. That means I put SN in excess. Obviously, that means I2 is the limiting reagent. Right? That is what we understand from this statement. Obviously, even after the reaction is completed, even after the reaction is completed, there is some amount of SN left out. Obviously, that means that is in excess. So I2 will be the limiting reagent. Yes, tell me, Kana.
so we are assuming that the reaction is 100%.
Yeah, there is nothing given to decide whether any percentage efficiency. So nothing is given. We assume it to be 100% complete. Yes, correct.
Okay, sir.
That means this value will become 0. That is, whatever be the amount of I2, this will eventually become 0 after the reaction is over. But this is not going to become 0, not because it's 100% completed, but because SN is the excess reagent. That's all. Right? Okay, do it. This problem looks complicated, but it is not. It's a very simple problem. You have to approach it correctly. Okay, and nobody is asking what is the atomic mass of tin and what is the atomic mass of iodine? Nobody knows, and still you're doing the problem. I don't know how you are doing it. So for
The mass
iodine
of iodine
is
is
127. 127 grams. For tin, it is 119 grams. That's the atomic mass of tin. Yes, please do not sit idle. Again and again, I'm telling you. If you're not going to try, you will not even know whether you don't know or not. Only if you try, you'll know. Okay, this I don't know, this I know. Right? Right. The answer, guys.
Sir, I tried, sir, but I'm not sure how to do it.
Sure. Okay, let me help you. Fine, I think I will do. See, looking at the question, if you get paranoid, if you get afraid, that 90% of chance that you will not get the answer. Now itself, I'm telling you, by looking at the question, if you get afraid, that's it. Every question is easy. Every question, there is a solution. All you have to do is approach it calmly. You will get the answer. Okay, fine. Now, the first step would be to write the reaction first. Okay, so how I write Sn plus I2 form. They're telling that Sn and I2 is forming SnX Iy. Right? Now remember, you have to balance this equation very properly. Right? So how will you balance? I have X Sn, so I'll put X here. Now I have Y here. I already have 2, so I'll put Y by 2. No issues? Till now, no problem. X Sn plus Y by 2I gives SnX Iy. Done. Okay. Now they have given what? They have given 1.947, right? I have given 1.947 grams of iodine, and also they have given 1.056 grams of tin. Okay, and I know this is an excess, right? So eventually this is going to become 0, but this I have, they are told that they are having 0.601 grams of tin still left out. Okay, right? Now I can actually calculate how much is undergoing the reaction, right? So Sn reacted would be what? 1.056 minus 0.601. No issues, guys? How much amount of S? This is the amount left out. This was the total amount. So obviously, how much has reacted is this much, right? And if I do this, I think it is going to be 5. 6 minus 1 is 5.
0.455.
0.455.
Yes, sir.
Okay, so 0.455 grams. So now, like along with this, I write 0.455 grams is only required of Sn, and this much amount of I2 is required. No issues. Okay. Now, please understand, whatever be the number of moles of iodine I have here, right? Now I have to convert number of moles, right? I'll convert it. Now, whatever be the number of moles of iodine here, that many number of moles of iodine should be here also, right? Anyways, if I just calculate the number of moles would be 1.947 divided by 127 into 2, right? Because the I2, not I, right? So it will be what, 254, right? So 1.947 divided by 254 is the number of moles of iodine I have here. Okay, right. Same way I can calculate, fine, no issues, right? So now what I understand is I do the stoichiometry. How do we do stoichiometry? I write it like this. Now, like, see, forget about Sn because that's the excess reagent. I have to count only I2 and this. Okay, now how do I write? Y by 2 moles of I2 gives 1 mole of SnX IY. Is it not? The stoichiometric coefficient here is 1. Right. So Y by 2 moles of I2 gives 1 mole of 1 mole of SnX I. Correct? Right. So now how many moles I have? I basically have 1.947 divided by 254 moles of I2 will give how many moles? No issues. Okay. Now, what I understand is I have Y moles of I here. If I can find what is this Y, the Y, same Y only will come here. Correct? Right? Now you can easily, I will not call it as X because X is already there. So I call it as A moles. Some A moles of SnX Y is getting formed. Okay. So what is that A? You can easily calculate. That will be 1.947 divided by 254 into Y. Okay, right, fine. Anyways, we'll not try to complicate it, right? So what I understand is I have this way, y by 2 moles gives 1 mole. So this many moles gives how many moles? If I calculate, actually I'll be able to find it out, right? So that would be this much. This into Y by 2. Okay, then what we can do? One second. Just give me a moment. Y by 2 gives 1 mole. So this many moles gives A, and that I'm getting in terms of Y. Okay, fine. We'll keep it as such, right? We will keep it just as such. We'll not do anything. Okay, so I have a connection between A, that is the number of moles of SnXY formed, with Y. Okay, now I can do the same calculation with respect to Sn, right? But I should not use 1.056. I have to use only this value, that is 0.458, because that much only is reacting. Rest of the amount is still unreacted. Okay, so I can write like this. What can I write? X moles of Sn gives 1 mole of SnX IY. Now, how many moles I have? I basically have, now if I convert this into number of moles, this will be 0.455 divided by 119, right? That will be the number of moles. So that would be 0.455 divided by 119. That is the number of moles of Sn, right? Will give you same A moles only, because whatever be the number of moles of SnX formed because of Y by 2, same amount will be formed because of X moles of Sn only. X moles give 1 mole, Y by 2 gives 1 mole. So I can write only A moles. Whatever A I wrote here, right? The same I can write A. Okay, right? Now what you have? I have A. I'll be able to calculate as, I think I'm doing something wrong. What am I doing wrong? A into this. Oh, sorry. This should be 2 by 1. Because you understand this into this into this. Okay, so if you have to find A, this would be the case. Okay, right. So this A now will become 0.455 divided by 119 into 1 by x, right? Into 1 by x. Okay, so this also we have. Okay, fine. Fine. Okay, this also I understand. Correct. So what if the mass of Sn plus mass of I2 should be equal to the mass of Snx Iy, because a law of conservation of mass. So what I'm trying to tell you is that 0.455 grams, that is the actual amount of Sn reacting, plus this is Sn, plus 1.947 grams, that is I2, is forming SNX IY. So now if I add these two, that is 0.455 plus 1.947, if I, how much will I get? 0.455, 1.947, 10 times. This would be 13, 14 times 2.402 grams of SNXIY I can have. Very simple, no guys? I think nothing I did. Right? These two are stoichiometries in terms of X and Y, and this is just law of conservation of mass. Okay, so I basically have this A. Now I can write in terms of this A is nothing but number of moles. Now I can write it in terms of this given mass by molecular mass. I know the given mass. Given mass is 2.452, right? Okay, so look at this. A, I can write it like this: given mass divided by the molecular mass. Molecular mass I don't know. Let me write it in terms of X. How will you calculate the molecular mass? It will be, can I write it as 119 into X plus 127 into Y. Now, hope you understand how am I writing this. For example, if you have Al2O3, how will you write? It will be 2 into atomic mass of iron plus 3 into atomic mass of oxygen. The same thing I wrote. Instead of 2 and 3, I have X and Y. That's the only difference here. Okay, so A is nothing but 2.402 divided by 119. This is given mass, molecular mass. Very simple, right? Now I have two equations here. You can see, right? Now A in terms of Y and A in terms of X. Correct. Now again I have this A, you see, in terms of X and Y. Okay, let me write actually. Like I have A, say I call this as the first equation. Right, now second equation is this, that is A is equal to 1.947 divided by 254 into Y by 2. Okay, now instead of A like this, I write A with respect to this now. Okay, I rub this A and I write this one, whatever is there, I write it here. So that would be 2.402 divided by 119 into X plus 127 into Y. Okay, which is equal to 1.947 divided by 254 into Y by 2. Done. Okay, now you have another equation which is here. A is equal to this much into this thing. Right, again I can write the same thing, that is 2.402 divided by 119x plus 127y is equal to this one, that is 0.455 by 119, right?
Sir,
119.
could you go to the previous page 1 second?
One second, sure. Right? Previous page is this one?
Yes, sir.
Yeah. Please, sir. What is the doubt? Maybe if you can little make it smaller and everything will be visible. Yeah, I think now this will be fine.
Sir, in the equation which you wrote on the right side, you wrote y by 2, sir.
Y by, oh, here I wrote y by 2. Oh, I'm sorry, this is 2 by 2. Okay, sure. Into 2 by 1. Okay, right?
Yes, sir.
Yeah, cool. That's it, guys. I think I've solved the question. Now you see, this is equation 2, this is equation 3. You have two equations and two unknowns only. What are two unknowns? X and Y are the only two unknowns I have. Okay, now I'll just repeat what I exactly did. See, the first step is to write the equation very properly, right? X Sn plus Y by 2 I2 gives Sn X Iy. Right now, they have given this much amount of Sn reacts, this much amount of I2 reacts, but in that only 6.01 grams of Sn is unreacted. How much is reacting is 0.455. Okay, now I do the stoichiometry connecting I2 and Snxy and Sn and Snxy. So I got two equations, right? I don't know the number of moles of Snxi formed because all it in terms of X and Y. So I got two equations here. Now, next thing what I did is I used the law of conservation of mass, right? Whatever amount of Sn reacting and whatever be the I2 reacting, the same mass should be there for Snxiy also, right? So now this A, which we wrote here, which is the number of moles of Snxiy, will be this much given mass by molecular mass, right? So now I have this A, I put this A in terms of X and Y in the two equations. Okay, and then you will be able to find X and Y value easily. Done. Okay, there should be a smaller method than what I'm doing here. If you're going to come up with a smaller method, well and good. Okay, now this equation you can solve, right? Say I write, I get Y only here, Y in terms of X, and substitute the Y value here in terms of X, you'll get the X value. Very simple. Okay, we'll not go into the details. Maybe I'll give you the direct answer. Right, the answer would be SNI4. Basically, X is 1 and Y is 4. That is what you'll find out. Okay, right? Simple question. Cool. Any questions, guys? Any problem anybody face? This I didn't understand, that I didn't understand. Anything, any problems here, what we did? Okay, it's just that the calculation will be a little difficult, nothing else.
Sir?
Yeah.
Sir, could you explain that stoichiometry that you did?
Yeah, sure. Right. So you see, first I connect I2 and Snxy. Right. So from the stoichiometric equation itself, we will write the first statement: Y by 2 moles of I2 gives 1 mole of Snxy. Right. Now I know what is the mass of I2 reacting, so I calculate the number of moles. Okay, fine. I calculate the number of moles. So for that, how many moles of Snxy? So I cross multiply and find out A. Same way, I have X moles of Sn gives 1 mole of Snxy. The statement is here. Now for this many mass, so this many moles, how many moles? A, same will be formed. So now that is the value here. And then I went for law of conservation of mass, got the A value in terms of X and Y, substituted here, and I got the answer as SNI4.
Okay, sir, got it.
Right? Okay, cool. Fine. I think we have spent enough time on these kind of questions, people. Stoichiometry, right? Okay, now the last part of the chapter, right? The last part of the chapter is going to talk about this process called as titrations.
Titration.
I think someone has to unmute. Please check everybody is unmuted or not. Fine. Now it's okay. I understand that you are so excited. Fine. Okay. So fine. What do you mean by titrations? Right. Now, titration is a process. Right. It is a process by which a solution, or I would say a solution's unknown concentration can be found out. Okay, so what is titration? Titration is a process by which I have a solution whose concentration I don't know. So if I do this process, that is, if I do titration, I will be able to find the unknown concentration. An unknown concentration, majority of the times, will be molarity. Okay, unknown concentration will be molarity. Okay, now before we move on to see how is the process and how is the other stuff, now let me do a very simple thing. Okay, now I have this equation. I am going to have NaOH and HCl reacting. Okay, NaOH and HCl reacting, or I will take NaOH and H2SO4, whatever it is. Okay, now let me write the equation here. NaOH plus H2SO4 will give me Na2SO4 plus H2. Okay, I think 2 moles of H2 will be formed, and I require 2 moles of Na. So that's the balanced equation. Yes, no issues, people. Right. Now I told you the data, right? For you to do stoichiometry, the data can be given in terms of mass, in terms of number of moles, or it can be also molarity. Okay. Now I tell you like this. I have H2SO solution is known. Assume that. Okay, H2SO solution, everything is known. So I say that I'll write 100 ml of 2m solution of H2SO4 is used. Okay, 100 ml of 2m solution of H2SO4 is used. Okay, now I use 200 ml of some m, like some concentration, some m I have. Right, I am using a 200 ml solution. That volume can be easily found out. You can measure the volume. Correct, but molarity you cannot be able to directly measure it. Okay, so what I'm trying to say is I have 100 ml of 2m solution of H2SO4, okay, and I have some 200 ml of NaOH whose molarity is not known to us. Whose molarity is not known to us. Will we be able to calculate this unknown molarity? Is the question here. Okay, now we will be able to easily calculate just by doing the stoichiometry, just by using the stoichiometry. Right, now very simple, right? Now we know the formula for molarity. Molarity is equal to number of moles by volume. If it is in ml, I put 1000. So n by v in ml into 1000, that is what is molarity. Okay, now I know, see, I told you whatever data is given to you, molarity is given to you, mass is given to you, volume is given to you, whatever be the data, the first step in stoichiometry would be to convert the data into number of moles. Okay, now, so the same thing has to be done here. I have given molarity and volume. So somehow you convert this data into number of moles. And you can easily see from the formula. What will be the formula? Number of moles will be equal to molarity into volume, if it is in ml, divided by 1000. Will be the number of moles. Correct? Molarity into volume will be the number of moles. Okay, fine. Now, I can easily calculate the number of moles of H2SO4 now. What will be the number of moles of H2SO4? Now, number of moles of H2SO4 would be molarity into volume divided by 1000. That is basically 100 into 2 divided by 1000. Okay, so it will be 1 divided by 5. 1 divided by 5 will be basically be 0.2 moles. No issues. I calculated this. Okay, 0.2 moles of H2SO4 is there. That is, by I calculated 0.2 moles from the calculation. By knowing we know the molarity, we know the volume. So we use this formula to calculate the number of moles. Done. Right. Now you can do the normal stoichiometry. Correct. Now what you can find is the number of moles of HCl required. Okay. Now how to do stoichiometry? I write 2 moles of NaOH. I require how many moles of H2SO4? Only 1 mole. 1 mole of H2SO4. Now, how many moles of H2SO4 I have? I found that I have 0.2 moles of H2SO4. So 1 mole of H2SO4 requires 2 moles. So 0.2 moles. If I have 2 moles, if it would have been 4 moles, now this would have been 0.4 moles. Yes, or if at all you're not able to find this data, cross multiply and find out. X, you put X here, and then you can get the X value as 0.4. Okay, now what I have is, I found out that I have 0.4 moles of NaOH required. Okay, now what is the question? I need to find what is the molarity required of this particular NaOH solution. I don't know the molarity, correct? Right? I know the molarity and volume of H2SO4, so I calculated the number of moles. I did the stoichiometry and I found the number of moles of NaOH. But what we need to find is the molarity. Again, use the same formula. Molarity is equal to number of moles by volume into 1000. Molarity we don't know. Correct? Molarity we don't know. Number of moles, just now we calculated for number of NaOH, that is 0.4 moles. Divided by volume. Volume is how much? You can see the volume is 200 ml for NaOH. 200 ml into 1000. So this into this, I mean, will become 5 times. So this into this will become 2m. That's the answer to this question. Okay. Now, why did I do this? Is because I'm just letting you know that the data can be given in terms of molarity and volume also. If they give you molarity and volume, convert them into number of moles, do the stoichiometry, again find the molarity of the unknown solution. Right? If you do the stoichiometry, you'll get the number of moles of this particular solution, whatever we need to know. And from the number of moles you found out, volume will be already given to you. You find the molarity. Or in some other question, they will give you the molarity and ask you to find the volume. Again, same procedure, except that the formula has to be used differently. Okay, right? Any questions you have? Anybody has any question? What we did here, right? We first converted this in number of moles, stoichiometry, and find the molarity. That's it. 3 simple steps. Okay, right? Fine. Now this is exactly what we do in titrations also. Now we understood the mathematics part of it. This is exactly what you will do in your labs also. Okay, you will write the equation, balance it, everything what we do exactly we do. Now this is the mathematics part, right? Now what we have to understand is the experimental part. How do we do the experiment? Right? How do I know that I'm preparing only 2m solution? How do I understand that I have only 100 ml? How do I understand I have only 200 ml? How do we know all this? Right? That is where the experimental part comes in. Okay, guys, give me a moment. I'll be back in 1 minute. I'm sorry. Just give me. Okay, I'll continue. Right. So I was talking about, and we now understood the mathematics part. How do we do the calculations? That is very easy, right? But how do you do the experiment part? How do you do the titration is what is important. Okay, we'll go into it. Right. Okay. So in titration, people, right? Now there are 2 steps. One is what is called as titrate, and the other one is what is called as titrant. Right. Now this titrant I know both molarity and volume. Okay, for the titrant, I know the molar. This is the known solution. Titrant is the known solution, right? And this titrate, we don't know the molarity, right? And volume, I'll tell you how to calculate this. Okay, sometimes volume is known, molarity is not known, or sometimes molarity is known and volume is not known. Depends on the question. Okay, but for titrant, right? For that, I know both the molarity and the volume. So I can understand from this. In this case, I have given you both the volume and molarity of H2SO4. So this will become the titrant, right? And for this, we are calculating. So this will become the titrate. Okay. Now the titrate can also be called as analyte. Right? Titrate can also be called as analyte. Basically, we are doing the analysis for a particular compound. That compound is what is my analyte. It is also called as titrate. Okay, fine. Now we'll come back to find how to find the molarity and volume later. We will spend some time on this titrate. Okay, we'll spend some time on this titrate. Okay, now the first step is to prepare the titrant, right? For you can see here, I told you that I have 100 ml of 2M solution of H2SO4. How do we first prepare this? How do I get 2M? How do I get 100 ml? All this is the question which you'll ask me. Okay, so for that, we are not calculating anything. We are going to prepare it, right? We are going to prepare the solutions. Okay, right. Now, see, I have something called as a standard flask, right? Inside the standard flask only, I will have the titrant, or I will call it as standard solution. Okay, I have something called as a standard flask, and inside the standard flask only, I will have the titrant, this one, for whom I know, right? And the solution inside it is what is called as standard solution. So you have to first prepare the standard solution. Okay, now the standard flask will be something like this. Okay, and it will have a marking here, right? Now, depending on the flask, the marking will give, say, 100 ml or 200 ml or for 10 ml. It can be anything. The flask, depending on the marking, depending on the size of the standard flask. This is standard flask, right? This is a standard flask. Now, the marking will tell you what is the total volume of this. Okay, fine. Anyways, now assume that I have to prepare. We will take the same example. I want to prepare 2M solution, 100 ml of 2M solution of H2SO4. I have to prepare this. Okay, I write it here. Okay, I have to prepare 100 ml of 2M solution of H2SO4. Right, I have to first prepare this. We'll try to understand how do you prepare this. Okay, now this 100 ml you leave. First, we'll concentrate on this 2M. Okay, now what do we forget about? I told you that forget about this. Now, if I say 2M, that is molarity is 2, what do I understand? I understand that 2 moles of H2SO4 is dissolved in 1 liter of the solution. Yes, this is coming from the definition of molarity, right? 2 moles of H2SO4 is dissolved in 100 liter of the solution. Right? And for 2 moles, you can calculate what will be the mass of H2SO4 also. Can I say it will be 2 into 98 grams? That is 2 into 98 will be how much? 196 grams of H2SO4 should be dissolved in 1 liter of the solution. Okay, so for 1 liter, if I want to make 1 liter of this entire solution, I require 2 moles of H2SO4. Or I would say 196 grams of H2SO4 is required to make 1 liter. Okay, now say assume that the standard flask is 100 ml. Okay, the standard flask is 100 ml standard flask. I told you, depending on the size, the volume will vary, right? So the standard flask given to you is 100 ml. Okay, right? Fine. So what I understand is if I need to have a 1 liter solution, right? I should have 2 moles of H2SO4 dissolved in it to form a 2M solution, right? So I'll write it like this. I write 2 moles of H2SO4 for 1 liter of solution. But in the standard flask, what I have? In the standard flask, I have only 100 ml. Instead of 1 liter, can I write this as 1000 ml? Right? I have 2 moles of H2SO4 required for 1 liter to form a 2M solution, right? So now I have only, say I have a 100 ml flask. So I convert this liter into ml. So I have for 1000 ml, I know 1 liter is 1000 ml, right? So for 1000 ml of solution, I require 2 moles of H2SO4, or I can write 196 grams of H2SO4, right? So how many ml I have now? I have 100 ml. Okay, I have 100 ml for this, how much, right? So for
Sir?
1000, yeah.
Sir, assuming that the solution is homogeneous, then can't we just take 100 ml from the 2M solution?
100 ml from the 2M solution. First, you have to find. See, 2M solution, it is not directly given to you. You have to prepare it. That's what I'm telling. How do we prepare? That is what I'm telling. Are you able to understand?
So no, sir. What I'm telling is, so first we prepare the 2M solution of H2SO4, that is
Okay.
dissolving 2 moles in 1 liter of solution, and then
Correct.
take 100 ml from that solution.
Absolutely, we can do that. Absolutely, you're right. But the thing is, we generally will not have 1 liter standard flasks, right? We will have only 100 ml, 200 ml, 500 ml. 1 liter flasks are very rare. Okay, but if you have a 1 liter
okay,
flask,
sir.
right? If you have a 1 liter flask, absolutely, what you're telling is absolutely correct. Okay, right.
Okay, sir.
Fine. Right. Okay, fine. So we understood that for 1000 ml of solution, we require 2 moles of H2SO4. So for 100 ml, how much we require? We require, can I say it will be 0.2 moles? Okay, 0.2 moles of H2SO4 is required. Okay, now I don't want this 100 ml here actually. I want only 10 ml, assuming that I change the question. Okay, I require 10 ml of 2M H2SO4. Okay, fine. Now we understood. For the standard flask, I told you it is 100 ml standard flask. So for me to form 2M, I would say 100 ml of 2M H2SO4, right? I require 0.2 moles of H2SO4. Guys, do not get confused. I'll repeat you again very slowly. See, the task for us in our hand is to prepare 10 ml of 2M H2SO4. And this 10 ml of 2M H2SO4 is going to react with NaOH. Okay, right. Now, forget about this 10 ml. We'll see about it later. Now, first thing is I have to prepare 2 ml, molarity of 2 of H2SO4. Right. So now I understand from the definition that 2 moles of H2SO4 should be dissolved in, or 2 moles of H2SO4 should be there in 1 liter of the solution. Okay, now I don't have 1 liter flask with me. What I have is only 100 ml flask. Okay, so for 1 liter, if I have to put 2 moles for 100 ml flask, how many moles I have to put? That is 0.2 moles. Okay, so 0.2 moles into 98, which will become how much? 19.6 grams of H2SO4. Now, this 19.6 grams will be measured in a weighing machine. You know weighing machine, right? I will take some H2SO4. I will add 19.6 grams of H2SO4 to that. Okay, right? 19.6 grams of H2SO4 I add, and to this I had 100 ml of water. To this I add 100 ml of water. So what will happen? Basically, I am going to get this particular thing out. Is it not? Right? I hope everybody understood. For 1000 ml, I require 2 moles. For 100 ml, I require only 0.2 moles. 0.2 moles basically means 19.6 grams of H2SO4. 19.6 gram I measure in a weighing machine, right? And I add sufficient amount of water till, say, basically, I measure the 19.6 grams H2SO4. I add it into the flask. Okay, I add it into this. Then I add water. I keep on adding water till I reach this point. That means 100 ml. Okay, so what have we prepared? We have prepared 100 ml of 2M H2SO4. Till now, everybody is okay. I want everybody to tell me yes if they understood. Is it okay, guys?
Yes, sir.
Yes, sir.
Okay, 1, 2. I want everybody to tell me yes. I just want for my satisfaction. Yes, everybody understood, people. What are we doing here? Or if anybody wants to explain me, I mean, wants to get explained again, I can again do it. I got 3. What about others? Is everybody okay? What happened? Are you guys there? So what should I understand? I should understand that you didn't understand, or whether you understand. What should I get from this? Guys, please open up. Did you understand what I'm trying to say?
Yes, sir.
Okay, 4, 5. Okay, I have almost, I have 11 people here. Out of them, only 4 understood. Rest of them understand. Is that what I have to get from this? Okay, so if you're not going to speak, people, I will not understand whether you understood or not. Okay, then I'll keep on repeating the same thing again and again, assuming that you didn't understand. Okay, fine. I hope everybody is understanding, even though you're not opening your mouth, right? You hope you understand what exactly we did here. We require 2M solution first. So we prepare the 2M solution, but we know like 1 liter solution is 1 liter flask is not given to us. Only 100 ml flask is given to us. So accordingly, instead of adding 2 moles of H2SO4, we add only 0.2 moles. 0.2 moles is basically 19.6. We measure 19.6, put it inside the standard flask, and you keep on adding water till this point, till the marking. That is basically 100 ml. So we have prepared 100 ml of 2M H2SO4 solution. No issues, guys. Right? Okay. Now, see, from the standard flask, this is the standard flask containing 100 ml of 2M H2SO4. But how much I require? I require only 10 ml. Right? I require only 10 ml. So for this, there is another kind of vessel called as a pipette. Has anybody heard this word pipette before?
Yes, sir.
Sir.
Okay, right. So pipette will look like this. Okay, bear with my diagram, people. Right? Okay.
So is it like a dropper kind of thing?
Yeah, something like that. I mean, it's a very bad drawing. Sorry. Okay, so both the ends will be open. This end is open. This end is also open. Okay, and I will have a marking here. I will have a marking. Okay, now again, depending on the pipette, right? Depending on the pipette, the volume is different. Say in our case, assume that I have given you a 10 ml pipette. That means till this marking, if I'm going to fill, it is going to be 10 ml. That's what you understand. Okay, till this marking, if I fill, that is 10 ml. Okay, so what are you going to do is you are going to take the pipette. I think you have to look at the video. I mean, look at my video, guys. Right? So the pipette will be like this. Right? Okay. So what you do is you hold one end of the pipette in your mouth. Okay, this part, right? This part, or the top part, right? The top part you hold in your mouth. Okay, then you put this, right? You put the pipette into the standard flask. The standard flask is like this, right? I'll draw the diagram. Okay, this is my standard flask, which has this 100 ml of 2M H2SO4. Okay, right. Now what I do is that I keep it inside the solution. I keep this pipette inside this standard flask and I suck. I suck. How do you drink juice with a straw? Right? Like that you suck. Right? So when you suck, what will happen? From this, the solution will go inside. Right? But you have to be very, very careful, people. If you suck too much, the solution will go inside your mouth because you're sucking. There is no this thing here. You have to suck it very slowly. Right? So when you suck it very slowly, the solution will, this solution in the standard flask will go into the pipette. Okay, now it will reach this point, right? When the moment it reaches this point, you take out the pipette and you close the open end with your thumb. Hope you understand. So first thing is you took the pipette, put it inside this, and you suck from here. This is where you keep your mouth and you suck, right? And you have to be very, very careful so that the chemical doesn't go inside your mouth. Okay, right. So now when the solution reaches this mark, that is the 10 ml mark, you take out, and the moment you take out, you have to close it. Right? You have to close this part with your thumb. Right? Here is your thumb. Right? You have to close it with your thumb. Okay. Now if you take out the thumb, again it will go out. Right? So you have to keep on holding the thumb, closing it. Okay. Now what you have to do is that you transfer it. Like you have the thumb here holding the pipette, which is having 10 ml. You take the pipette. Right? You have the thumb closed here. You open the thumb. Now what will happen? Whatever is there, I am going to get it here. So what is here basically? 10 ml of 2M H2SO4. Very simple now, guys. This solution here, I had 2M solution of 100 ml. Right? From this solution, I sucked with the help of the pipette and I got 10 ml and I transferred this here to another vessel. That is 10 ml of 2M H2SO4.
Sir?
Okay? Yeah.
Sir, in the 100 ml flask, we can also prepare 10 ml solution, right?
Depending on the standard flask. Yes.
Sir, then we don't need to prepare 100 ml first, right? We can directly prepare 10 ml.
Correct. But if I need to have 10, for example, you need to have the measurements perfectly. Correct. Say if I have a 10 ml standard flask, then it's okay for me. Hope you understand. This standard flask, what I used here, sir. I told you it was 100 ml. But if this was a 10 ml flask, yes, you would have prepared. Right? If this is a 1 liter flask, accordingly you would have prepared. So depending on what is available to you, accordingly you will prepare. That's the thing here.
Okay.
Okay. Okay. Right. So I had 2M solution of 100 ml of 2M solution of H2SO4 in the standard flask. I prepared it. Okay. Now out of this, I require only 10 ml. Right? How do I take 10 ml? Use the pipette, suck it till this point, then close your thumb after you take out of your mouth, and then take it to the next solution, open it. Now what will happen? All these things will go out. Now what I have in this vessel is basically 10 ml of 2M H2SO4 solution. Okay, I hope everybody is able to understand what I'm trying to say, right? So the titrant part is over. Right, we have prepared what is required. See, we wanted 10 ml of 2M H2SO4, right? So we took, depending on the standard flask, we took, I told you that it is 100 ml standard flask. So I have to prepare 2M solution means I have to take 19.6 grams of H2SO4. Again, the calculation comes from here, how we have to take and all. Okay, so I can repeat it again if you want. For 1 liter solution, I require 2 moles because that is coming. Now, how did I write this? This is coming from 2M. I know the definition. Now, molarity is nothing but number of moles of solute present in 1 liter solution. Right. So for 1 liter solution, I require 2 moles. But for 100 ml, I require only 0.2 moles. I know 0.2 moles. What will be the weight? I measure it. I put it inside the standard flask and keep on adding water till I get till this point. So that's it. I have prepared 100 ml of 2M H2SO4. From this, I require for my experiment, I require only 10 ml of the solution. How do I take 10 ml? That is where the pipette comes. Right? Pipette, you suck it, it will go inside till this point. Hold your thumb after that. Now, when you transfer it to the other vessel, you open the thumb to get 10 ml. Okay. Now, for example, this pipette, right? This pipette was only 5 ml pipette. Okay. This pipette which was given to you was 5 ml pipette. Then what you have done?
So we carry the process 2 times.
That's it. Very simple. We do first 5 ml, transfer, open the thumb. Again, you suck, transfer, thumb open, 5 ml. So like that you do. Okay. Right. Fine, like that.
Sir?
Anyways, depending on the, yeah, please tell me.
Sir, so titration is basically for practical purposes.
Yes, obviously it is for practical purposes, right?
Okay.
Like we have to find the unknown concentration. All these are practical purposes. Yes. Okay. So guys, the titrant part is over. The preparation of titrant part is over. First, you form the standard solution. From the standard solution, you take the pipette and you take the required amount. As simple as that. Okay. Right. Now what you have to do? What is the time? Okay, we still have half an hour. Right. So now what you have to do? Now the titrant part is over. Now how do we measure? Now the question was to find the molarity of this NaOH. Okay. Now I took 110, 100 and 200 ml. Let me take its 10 ml and 20 ml. Okay, fine. Anyways, right, we'll go for it. Now we have finished the titrant part. Okay. Now the titrate, right? So I have some volume, some V ml of some M NaOH. Okay, right. Now, guys, what you do is this unknown NaOH solution, right? This unknown NaOH solution will be put inside a vessel called as a burette, right? Pipette, burette, standard flask. Three things are there. Standard flask is for preparing the titrant, right? Then pipette is used for transferring the required amount, right? Now burette is going to hold the titrate, right? The burette is going to hold the titrate. Now how does a burette look? This is how a burette looks, right? There'll be a tap kind of stuff. Okay. Now this vessel will be kept like this vessel, right? This contains 10 ml of 2M H2SO4. Okay. Now this burette will contain the markings, right? These markings are nothing but volume markings. Okay. So it's starting with 0, 10, 20, 30, 40, 100, like that it will be. Okay. These markings contain the volume. And inside this, you put the unknown NaOH solution. Okay, unknown NaOH solution. Okay, fine. Now, all we have to do is what I have to do is you have to open, this is the tap. Okay, all you have to do is slowly open the tap, right? So that drop by drop by drop, the NaOH goes into this H2SO4 solution. Okay, open that. You should not open it very strongly, people. Very, like say, if you don't open it too much. If you open it too much, the experiment will not be coming properly. You have to open it so very slowly, slightly open it, so that drop by drop by drop, NaOH goes into the solution. Okay, right. Now, obviously the reaction is going to happen. What reaction is going to happen? Neutralization reaction is going to happen. NaOH and H2SO4 are going to react to form Na2SO4 plus H2O is going to happen. That reaction is going to happen for sure. Okay, now how will I understand whether the reaction is over or not? Obviously, the starting reaction will keep on happening, right? But at some point of time, I have to know, like I have to know whether the reaction is complete or not. How will I know? For that, I have to use something called as indicators, right? Something called as indicators. Now, these indicators will show me once the reaction has gotten over. These indicators will show a change in color. I think you must have known in your 10th class acid, bases, and salts, right? Now, what kind of indicators I can use? For example, phenolphthalein, right? Phenolphthalein is an indicator which, can you tell me what will be the color in basic solution and the acidic solution, people? Phenolphthalein? What color?
Sir, acidic, I think colorless, sir.
Correct. Acidic, it becomes
And
colorless.
basic is pink.
Correct. Right. And basic solution, it is pink. Okay. Now there is one more thing. There is something called as methyl orange. Can you tell me what will happen if I have acidic and basic conditions?
Sir, acidic is orange.
Acidic is orange. Yeah, acidic. Yeah, acidic is orangish yellow, something like that. We can call it as orange or yellow in color. Okay. Now in basic solution, it becomes red. Okay, right. Methyl orange will be acid, will be yellow in color, and basic solution it will be red in color.
Sir, acid,
Okay.
can we say no color change?
Yeah, but sometimes there are different derivatives of methyl orange. Sometimes they will be orange color in acid solution. Sometimes they'll be yellow in color also. That's why I said orange or yellow. Okay.
Okay, sir.
Fine. Right. Now, these indicators are going to help me find out the end point. What do you mean by end point? Completion of the reaction. Very simple. Right? End point talks about the completion of the reaction. Okay, right. Now what I do is I have prepared this solution, right? 10 ml of H2SO4 solution. Okay, 10 ml of H2SO4 solution I have prepared, right? To this, before I put on the burette, right? Before I start the experiment, before I put drop by drop of this, before this, I put methyl orange. I put methyl orange in this. Okay, so obviously this will be an orange color solution or an yellow color solution. Is it not? Because this is acidic solution. H2SO4 is acidic, and I add methyl orange. Obviously, it will be orange or yellow in color. Okay, right, fine. Now what is going to happen? Now you open the tap, right? Slowly the reaction is going to keep on happening, right? The drop by drop by drop, the reaction will happen, right? Now, how will I know whether the reaction is completed or not? Obviously, when this orange color changes to red color, that means what? See, look at this. Now, the neutralization reaction will keep on happening, right? The neutralization reaction will keep on happening. So basically, acid and base will neutralize. Okay. Now, after a point of time, whatever be the H2SO4 would have been neutralized by NaOH, right? Now that becomes a neutral solution. That becomes a neutral solution. Now one more drop extra NaOH you add, what will happen? The neutral solution will become a basic solution now. Again, I repeat, people, right? So for this, okay, for this amount of H2SO4, some amount of NaOH would have come and neutralized this. Okay, now once it neutralized, I will get a neutral solution. No, not neither acidic nor basic. But if you're going to continue adding this, even one more drop of NaOH, what will happen? This neutral solution will become a basic solution, and obviously methyl orange in basic solution will be red in color. Right? That is the end point. Basically, the
Sir?
one more drop. Yeah.
Sir, what is the color of methyl orange in neutral solution?
Neutral solution also, I think it is not sure.
Sir, neutral means it won't change now, sir.
I think, yeah, it will still be in orange in color. Yeah. Neutral or
sir, but once it turns red color, then the solution become basic. No, sir.
Correct. Right. So it's actually what you're asking is, sir, that means I'm not doing the reaction exactly what it's required to be. I add some amount of this extra. NaOH will be a little extra. That's what you're trying to say.
Yes, sir.
Yeah, absolutely. So this is obviously an approximate method, what we are doing here. There are still more sophisticated methods we can use, but that is again not in your syllabus. Okay, so we just add one drop extra, only a very small drop extra, and that is enough for the color change to happen. So that is not going to mess up the calculation that much, because just one drop, one small drop. Okay.
Sir?
Yeah.
Sir, Hamsini told she isn't feeling well and she won't be able to continue the rest of the class.
Who is not able to continue, Kanna?
Hamsini.
Yeah, sure. Hamsini, you can leave, Kanna. No issues. Please go take rest. No problem. Okay, fine. So again, I repeat, guys, you prepared this 10 ml of H2SO4, you added methyl orange, it will be orange in color, right? Now you keep on adding this, there'll be a place where I get a neutral solution, just one more extra drop, right? Will convert this orange into red color solution, and that's it. You stop the tap, you close the tap. Okay. Now, initially assume that it was up to brim here, right? This was the marking 0. Okay. Now, obviously this would have keep on reducing as the reaction has proceeded. Now, assume that this thing is here. Say this is, I found out to be, say, this is 20 ml. Okay, if this value, right? The reduction, after the reduction, when the tap is closed, after the end point is basically change in color of the indicator, right? So after the end point, when I close the tap, this is the marking. That is NaOH, 20 ml of NaOH has reacted. Okay, done, guys. We know whatever we want. We know the molarity and volume of the titrant. We know the volume of the titrate. Now you go for the calculation. Do the stoichiometry. What's stoichiometry? You write the reaction. This is 10 ml of 2M solution. We know that. And I told you that this 20 ml we found out from the Burette reading. Now you do the stoichiometry. You will be able to find out what will be the molarity. If you want to explain again, it's very simple. To do stoichiometry, 2 moles of NaOH requires 1 mole of H2SO4. Now I found out that I have 0.2 moles from the calculations, molarity into volume. Yeah.
Sir, could you repeat how NaOH is 20 ml?
Yeah, sure. So where is the Burette? Right. So initially, when the tap was closed initially, you had 100%. That is, this is the 0 marking in the Burette. Okay. Now the reaction, the tap is open, the drop by drop will happen, right? The reaction will happen, that is neutral solution will form. Just one more drop, it becomes basic and the endpoint is achieved. Orange to red will happen. That time you close it. You close the tap. Now the reading would have gotten reduced because some amount of NaOH is keeping on going, right? Now initially it was here, now it will be here, right? Now this found out to be 20 from the reading I'm telling.
Sir, but this is the excess amount of NaOH, right?
No. That's why we start from here, 0. We didn't put 100 here. Please understand. Whatever be the amount, right? We start with 0. Say now, if this comes from here to here, that means 1 ml has reacted. If this comes from here to the next reading, 3 ml has reacted. If this comes from here to here, 4 ml has reacted. Like that, I'm telling 20 ml has reacted. Understood?
Oh, okay, sir. Yes, sir.
Okay, right. So like this, we found out what is the volume of NaOH reacted. Okay, then we go for the normal stoichiometry. Guys. Very simple, very, very simple. We convert the molarity and volume into number of moles. We calculate the number of moles of H2SO4, right? Then we calculate the number of moles of NaOH. Now I know the number of moles of NaOH and I know the volume from the Burette reading. You will be able to calculate what will be the molarity of the NaOH solution that is unknown to us. Okay, right? Guys, it's a very big process. First is preparation of titrant. First, you have to produce a standard solution. For standard solution, you do the measurement. You in the weighing machine, you take the salt or whatever it is, you prepare a solution. And then from that, you take the required amount with the help of a pipette and you transfer it to the, say this is called a titration flask. We can call this as the titration flask. Okay, from the pipette, from the standard solution, use the pipette, take 10 ml, transfer it to the titration flask and keep the titration flask under the Burette. And obviously in the titration flask, you will add methyl orange also. Okay, now in the Burette, you add the unknown solution, right? Water solution, I don't know the molarity. You add that, you add it up to the brim, 0 reading you add, and then you open it, drop by drop by drop, reaction will happen, end point will happen. Now when you stop the tap, there'll be a reading here, 20 ml or whatever be the reading, right? Now you go for stoichiometry. That's it. Very, very simple. Okay, guys, everybody understood? Is there any problem in any of the cases, any of the parts, any questions? Okay, I hope everything is clear. Right, now, if I have to do the opposite, right, now I'm going to ask you individual questions, right? Okay, right. Say, now I'm going to do the opposite, right? Say I have NaOH is known. Okay, that is, I know the molarity, I know the volume. For H2SO4, I don't know. Okay, for H2SO4, I don't know. Okay, now I want say 20 ml of 1 m NaOH solution. Okay, I require 20 ml of 1 m solution, 1 m NaOH solution. Right, now the standard flask given to you is say 100 ml. Okay, and the pipette given to you is 10 ml. Okay, pipette given to you is 10 ml. Okay, and obviously you have to find what is the molarity of this unknown NaOH solution. Right, now the first question is obviously you have to speak about the titrant part. Okay, now the standard flask given to you is 100 ml. Okay, now the question is, I'm going to ask someone. Chat. Oh, Raghav completely forgot about the class. No issues. You can look at the recorded videos. Fine. Fine. Can I ask Ashwath? Are you there, Kana? Ashwath? Are you there, Ashwath?
Yes.
Yeah. Yeah. So the question is, right now, everything you understood. Right. So I want to prepare 20 ml of 1 m NaOH. The standard flask given to you is 100 ml. Right. So first thing, what will you prepare? First, tell me, what will you do first? With the standard flask, what will you do? The starting point would be this 1 m. Or if I ask you for in the standard flask, first I'll prepare. Okay, first I'll prepare what? What will be the molarity? What will be the volume of NaOH in the standard flask? Can you tell me that? In the standard flask, what will be the volume? What will be the molarity? Yes, Ashwath, any answers? Okay, at least the volume you can tell directly is given, right? What should be the volume in the standard flask? Are you there, Ashwath?
100 ml.
Sorry?
100 ml, sir.
100 ml. Okay, that's right. I have, obviously it's given, it's 100 ml this thing. So the volume of the NaOH solution would be 100 ml. Okay, and what should be the molarity? What should be the molarity? That is also given to you. What is the molarity? I didn't hear what you said. Okay, fine. I think there's a problem with Ashwath. Maybe we'll go to the next. Harshita. Are you there, Kana? Harshita? Are you there, Harshita? I think you have unmuted, but I'm not able to hear you. Okay, fine. I think there's a problem again. Kanishk, are you there, Kana? Kanishk? What happened? Kanishk, are you there? You can, if you're not able to unmute yourself, you can put it in the chat box. Even Harshita, if you're not available, you can put it in the chat box. But you're there, I can see it. Harshita, Tarush, are you there? Sorry, not Tarush. Kanishk and Harshita, are you there? Okay, there's something in the chat. First, we'll prepare 1 mole of NaOH in 1000 ml. Yes, correct. Right? But we don't have, yes, correct. What you're telling is absolutely right. If I have a 1000 ml standard flask, then I'll put 1 mole. Right? Hope you understand here. Yeah, right. Kanishk, I'll ask you the next question. Next question, Kanishk. You work out the entire stuff. Sure. Right. So Harshita said, I have to prepare 1 mole. I should have 1 mole of NaOH in 1000 ml solution. Absolutely true. For me to have 1 M solution, right? For me to have 1 M solution, I should have 1 mole of NaOH in 1000 ml of solution. Absolutely true. Right. But Harshita, I have not given you 1000 ml flask. I've been giving you only 100 ml flask. So how many moles will you keep? Correct. Yes, we should find the number of moles for 100 ml. What should be the number then? For 1000 ml, 1 mole. For 100 ml? Easy, right? 10 is less. So that would be absolutely 0.1, right? So first what you have to take is 0.1 moles of NaOH. I can easily calculate the mass. 0.1 into 40, which will be 4 grams of NaOH I have to take. Right? Thank you, Harshita. Right. So fine, I have to take 4 grams of NaOH. Okay. And I have to put it in the standard flask. Right? Standard flask is here. Right? So this contains 4 grams of NaOH. Now I keep on adding water to this level because this is 100 ml. Okay, so this is 100 ml. So I add 4 grams of NaOH to this 100 ml. So now what I have prepared? I have prepared 100 ml of 1M NaOH. Correct? Right? 100 ml of 1M NaOH. Now what is the requirement? The requirement is 20 ml of 1M NaOH. Okay, so now I'm going to ask Srinidhi, are you there, Kana? Srinidhi? Srinidhi, are you there? Okay, I think there's some problem with Srinidhi. Fine. Madhumita, are you there, Kana?
Yes, sir.
Okay. So the thing is, we have prepared now 100 ml of 1M solution, right? 1M NaOH, but I require only 20 ml of this. And I have, what will you do then? I have 100 ml of 1M NaOH prepared. Now it is prepared, right? But
Yes,
out of this, sorry? Out of the 100 ml, I require only 20 ml. So what will you do? What instrument you should use now? What vessel you should use? What vessel you should use? Very simple, right? It's given. It's for transferring from 100 ml, I have to transfer 20 ml into the titration flask. So what should you do?
So?
Yeah. Yes, speak. I'm hearing. Again, there's some issue, guys. Madhumita, I know you're unmuted, but I'm not able to hear you. I think then there's a network issue. Okay. Fine. Maybe I will ask Subrajit. Are you there?
Yes, sir.
Yeah. So what should I do? For
Sir,
I have prepared
using
100 ml. Yeah.
Sir,
please tell me.
using pipette, since the pipette is 10 ml, we first suck the 10 ml like 2 times. So it
Okay.
becomes 20 ml of 1 m NaOH.
Okay, understood. So you are heard, no? And I'm not able to hear you, Madhumita. I know you're unmuting, but I'm not able to hear you. There is a problem with your mic or something else. I guess. Right? Fine. So as Supratit said, right? I require 20 ml, but the pipette given to you is only 10 ml. Right? So 2 times you have to suck and hold your thumb and transfer it to the standard flask. Okay, there is some other chat. Wait, I'll ask you one more question, Madhumita. Wait, put it in the chat box. Okay, the question is yours now, right? Now we have prepared, what is that? The titration flask, right? Titration flask is here. I have basically 10 ml, right? 20 ml, sorry, 20 ml. What happened? Okay, right? So I had 20 ml of 1 m NaOH. Okay, and the question is, Madhumita, what should be the indicator used? What indicator you will use here? Now you can put it in the chat box. I have prepared the solution, right? Now I have to go for the burette and stuff, right? Before that, I have to add an indicator. What indicator you will add, Madhumita?
Sir,
Yeah,
sir, could you go to the question 1 second, sir?
yeah, sure. Yeah, the question is this. NaOH is known, H2SO4
Okay,
is
sir. Okay.
unknown. Yeah. So yeah. Yes, Madhumita, what will be your answer? What should be the indicator which I should use? So you have to think about the color change and answer. I'm not sure. Okay, any guesses? Okay, no issues. Maybe I will ask.
Sir?
Yeah, tell me, Kana.
Sir, I had network issues, sir. Sorry.
Sure,
Is
sure.
it
Please tell me.
phenolphthalein, sir?
Absolutely, yes. We have to use phenolphthalein, right? I think the same answer I think is coming from yes. Thymol phenolphthalein. Okay, yeah, phenolphthalein. Thymol phenolphthalein is a derivative of phenolphthalein. Anyways, sure. We have to use phenolphthalein here, right? So we have to use phenolphthalein here. Now, when you put phenolphthalein, this is the basic solution. So this would be pink in color. Is it not? This would be pink in color. Okay, now that's it, right? I have to take the burette. I'm sorry, guys. This is a very bad drawing. I draw it again. Right, so I will have the burette, which will have the tap, and then until this point, I fill it with H2SO4, which is unknown to us. Okay, now I keep on add. I open the tap. I keep on adding it. Okay, I want maybe Vaishnavi. Are you there, Kana? Vaishnavi. Okay, I think she's there. Right. So Vaishnavi, when should I stop the tap? When should the tap be stopped in the burette? When it reaches 100 ml? Is it like that? You have to switch off the tap when the reaction gets over. How will you know whether the reaction is over or not? How do you know it's 100 ml? We don't know that, right? How will you know that the reaction has gotten over or not? and then only we'll switch off the tap, right? But how will we know the reaction has gotten over or not? Yes, any answers? If you're typing, I can wait, no problem. Okay, I think there's some problem. Okay, fine. Maybe I'll ask Navya. Are you there, Kana?
Yes, sir.
Yeah. Can you tell me when should I stop the tap?
Like the color changes into pink color changes into colorless solution.
Absolutely correct. Yeah, when the color changes, Madhumita, correct, right? As everybody said, with a pink colored solution will become colorless. Why? Because phenolphthalein is colorless in neutral solutions as well as in acidic solutions, right? So the pink color will become colorless, then you stop it. That's it. Now you would have gotten the reading, whatever be the reading. Say this was some 10 ml, something. I don't know, some random number I'm giving you. You have found out the volume, then you go for stoichiometry, do the calculations, then you will find the molarity of this particular solution also. Okay, so you will go do this in your labs when your school opens, right? Whatever exactly I told you, you will go do this in your labs, and at that time it will become more clear, right? So next class we will concentrate on doing these problems. Okay, problems are very easy actually. Understanding the experimental part is only difficult. Problem doing part is very normal stoichiometry, nothing extra. Okay, fine. I hope I can stop here. Right? Is there any other questions you want to ask people?
Sir?
Yeah.
Sir, the practical purpose of stoichiometry is titration.
Absolutely. Yes, that is the point.
Okay.
The practical
sir?
listing of the thing. Yeah.
Sir, in that problem, the number of moles of H2SO4 will be 0.02, right?
Yeah, because we changed the number now. Right. We change it from 100 ml to 10 ml, right? So obviously it will be 0.0.
Yes, sir.
Right. Oh.
Okay, sir.
Yeah. Any other questions, guys? Okay. Fine, guys. Thank you so much. We'll meet again next week. Until then, bye-bye.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.